So, we have been looking at non-unital sister algebras. We saw how to add identity to it and make it into a unital sister algebra, and we defined the Gelfand transform on a non-unital sister algebra just like we did for the unital case. And we saw that the space of linear functionals, multiplicative linear functionals, that is what we call the spectrum of A, sigma of A, is a locally compact Hausdorff space, right. And once we add the identity, of course, we get a compact Hausdorff space, and we are removing the point at infinity, we get a local, unless that point is isolated, we are going to get a locally compact Hausdorff space. And the Gelfand transform is a map from sigma A, from A to C0 of sigma A, that means continuous functions vanishing at infinity on this locally compact Hausdorff space sigma A. So, our aim is to complete the proof of the Gelfand Naimark theorem for non-unital commutative sister algebras. Okay. So, let us continue. Okay. So, let us start with the following theorem. Okay. Let A be a non-unital commutative Banach algebra. So, right now it is still Banach algebra. Then, so most of this we have already seen. Then sigma of A remember is the collection of all multiplicative linear functionals that can be defined even for non-unital case. Sigma A is a locally compact Hausdorff space, right, and it is a locally compact Hausdorff subset of A1 star. So, that is the unit ball in A1 in the weak star topology, right, weak star topology. If sigma A is non-compact, then the weak star closure of sigma of A. So, sigma of A sits inside the unit ball of A star, and if it is non-compact, then if you take the weak star closure, all that you are adding is the point 0. Okay. So, the weak star closure of sigma A is sigma A union 0, okay. And the Gelfand transform on A is an algebra. So, all this we already know, homomorphism, it is an algebra homomorphism from A into C0 of sigma A. Okay. So, C0 is important there because we have a non-unital Banach algebra, and it is into, as we have seen in the case of unital as well. We will see that it becomes a isometric isomorphism for a C star algebra, right. That is what happened in the unital case also. So, we have the spectral radius formula. If I look at the L infinity norm, that is the supremum norm of x hat. Remember, x hat is an element of C0 of sigma A, right. It is a continuous function on this locally compact Hausdorff space sigma A. The supremum norm of that is limit norm x to the n to the 1 by n, right, and going to, okay, for x in A. Okay. So, proof. So, we have already proved all this that sigma A is sigma A union 0 would be the compactification of sigma A and all that. These things we have already discussed, and the Gelfand transform is, of course, is an algebra homomorphism that we already know to C0 of sigma A. What is left to be proved is the formula, right, that the supremum norm of x hat, which is essentially the spectral radius, even though we did not define what spectrum is and so on. This is limit of norm of x to the n to the 1 by n. Okay. So, all we need is to prove the formula, right, which is the supremum norm of x hat, the Gelfand transform of x is equal to the limit. Okay. But this follows immediately. So, note that this is easy. Okay. So, note that you look at the Gelfand transform of x, x in A, and look at the supremum norm. Well, this is same as you go to the unit case. So, that unital case. So, you look at x 0 hat. So, x comma 0 is an element in the unital sister algebra A tilde, and the supremum norm of this and x hat are same, right, because the only difference between x comma 0 hat and x hat as that they are defined on two different spaces. One is defined on sigma of A, the other is defined on sigma of A union 0, right. But x hat is something which vanishes at 0, right. So, when I take the supremum, that particular value is not going to change anything, you are going to get this equality, and this you know is the spectral radius, because now you are in the unital case. So, spectral radius of x comma 0 in A tilde, right, and because that is the unital case and you know that, and this we have already proved. In the unital case we know that this is x to the n to the 1 by n. Well, strictly speaking it is the norm of x comma 0, but the norm of x comma 0 is norm of x, right. So, there is no difference between putting the norm on A or norm on A tilde, you are going to get this. Okay. So, because the norms coincide, because the norms coincide. Okay. So, that takes care of the first proposition. So, now we are in a position to write down the Gelfand Naimark theorem for non-unital sister algebras. Okay. So, we have already proved essentially all of this, all of that we need, just putting together everything. Gelfand Naimark theorem. So, if script A is a non-unital commutative sister algebra. Okay. So, we have a non-unital commutative sister algebra, then the Gelfand transform is a star isometric. So, it is supposed to respect everything, right. It will respect the star, it will respect the norm, and it is an algebra homomorphism. So, star isometric isomorphism. So, it is not just an algebra homomorphism, it is an algebra isomorphism, right. So, star isometric isomorphism from the non-unital commutative sister algebra A onto C0 of sigma of A. Okay. So, we have done most of this already, we just have to put together things to complete the proof. Okay. So, let us prove. So, first make A tilde. So, A tilde is A cross C, we attach identity like that, right. So, A tilde into a sister algebra, Okay. So, then A tilde becomes, A tilde becomes a unital commutative one, right. So, unital commutative sister algebra, and we have the Gelfand Naimark theorem for A tilde, right. Hence, the Gelfand transform, from A tilde onto okay. So, C of continuous functions on sigma of A tilde, right, is is a star isometric isomorphism. So, that is the unital version which we already know, right. Now, A contained in A tilde is a maximal ideal, whose associated linear functional is is 0 tilde, right. Remember, the 0 functional had a unique extension to A tilde. And so I have so let us see if I can draw some picture which will be make this clear. I have A tilde and I have C of I have A tilde and continuous functions on sigma of A tilde. Sigma of A tilde is compact, and I have this identification which is the Gelfand transform, which is 1 1 on 2 and which is a star isometric isomorphism, right. So, I am taking a maximal ideal here. So, there should be a maximal ideal here, right. What is that? That is the corresponding one which consists of all functions vanishing at the point at infinity, right. So, the corresponding maximal ideal in C of sigma A tilde is C 0 of sigma A, right. So, I mean this is same as all those functions in C of sigma A tilde. So, which is compact, but at infinity it is 0, right. So, I should write f at 0 tilde equal to 0. 0 tilde is the point at infinity for sigma I, right. So, remember the maximal ideals in the compact case, when x is compact T 2, you take a point and you look at all those functions vanishing at that point, right. So, all those points vanishing at 0 tilde, that is a maximal ideal, and that corresponds to A when you go back to the original C-star algebra, right, and that is all. So, A and C 0 sigma A, they are in isometric isomorphism, right, because you have the isometric isomorphism from A tilde to C sigma A tilde and you restrict it, right. So, so this finishes the proof. Okay. This finishes the proof. So, the main point is to identify A, the maximal ideal, as the set of function on the other side as set of functions vanishing at infinity. So, that finishes the proof of Gelfand Naimark theorem in both in the unital and non-unital case. Okay. So, just to recall, in the unital case you get a compact Hausdorff space, which is the collection of all maximal ideal space or continuous linear multiplicative linear functional, and then you have the Gelfand transform, which is a star isometric isomorphism, which identifies your abstract commutative unital C-star algebra with continuous functions on a compact Hausdorff space. Once you remove identity, so if you have a non-unital commutative C-star algebra, you can identify it with continuous functions vanishing on a compact non-compact locally compact Hausdorff space, right. That particular Hausdorff space is again spectrum of A, which is the collection of all multiplicative linear functions. Okay. So, there are two things which you should remember. We are going to use these theorems to prove spectral theorem in general. Okay. So, let us spend some time before we start spectral theorem. We will look at things look at some case where the I mean how Gelfand Naimark theorem can be used. Okay. So, start with, so let us say I have a normal operator. Okay. So, this is going to be an informal discussion. Okay. I will start with things formally soon. So, let T be a normal operator on a Hilbert space H. Okay. So, I have B of H, which is a unital but non-commutative C star algebra. But T is normal, so T commutes with T star. So, T star equal to T star T, right. So, if you look at the C star algebra generated by T, that is going to contain, so that is going to be a commutative C star algebra with identity, right. So, let A be the C star algebra generated by T star and identity. Okay. So, this is going to be sitting inside B of H, right. Well, how does it look like? So, if you have T, you should have T star, you should have T star square, you should have T star, T star T and polynomials in T and T star, right. But then you also have to take the closure of that, because you want a complete space and so on. So, think of polynomials in T and T star, and then you are taking the closure in the operator norm. So, that is essentially the description of the C star algebra generated by T and T star. And what Gelfand Naimark theorem we have done so far says that this C star algebra, so A can be identified with C of sigma A. Okay. But what is sigma A? Remember, this was something we did. If A is generated by T star and E, then sigma A is homeomorphic to the spectrum of that element, right. So, note that sigma of A is homeomorphic to spectrum of T, right. This is sitting inside the complex plane, and this is your compact Hausdorff space, right. So, the C star algebra generated by T star and E can be identified with continuous functions on spectrum of T. Okay. So, remember, spectrum of T is well defined, whether it is in A or in B of H, right. We saw that in the C star algebra case, it does not matter if it is a C star subalgebra or not, as long as we are in the C star algebra situation, spectrum is well defined. So, this tells me that, so if I take T here, then that corresponds to the continuous function identity function. Okay. So, this would be sigma T to C x going to x, or lambda going to lambda. Okay, lambda going to lambda. So, T square will correspond to, because it is a it is an algebra homomorphism, it will be lambda going to lambda square, that is the function, right. Any operator here will give me a continuous function here, right, that is the Gelfand transform doing. So, similarly, any polynomial in T and T star will give me similar polynomial in lambda and lambda bar, right. T star will go to lambda bar, right, because star has to go to the complex conjugation on the other side, which is the star operation on the other side. And what we can do is, you take the closure with respect to the norm, here you will get all continuous functions, right, and here you will get appropriate operators. So, for each continuous function you will have an operator. Okay. This is how the C star algebra generated by T looks like. Okay. And from here one can, so this is the next step, from continuous functions we have to go to bounded functions on the spectrum, and bounded functions will give us, so for each bounded function f we will be able to define an operator. Okay. So, just like the Gelfand transform correspondence here, we will have something similar for bounded functions and a algebra of operator here. Okay. So, here bounded functions. Okay. So, that will lead us to a version of the spectral theorem. Okay. So, that is what we are going to do formally from now onwards. So, that is the aim. Okay. So, but before we start things, let us look at the finite dimensional case once more. Okay. So, we will look at spectral theorem. Okay. So, we will use Gelfand theory to prove this. Okay. So, let us look at the, so revisit, let us revisit finite dimensional spectral theory. Okay. So, let us say T from Cn to Cn is normal. So, it is a normal operator, right. So, T star T equal to T star. You can think of them as matrices, but I will keep writing operators because that is what we are going to do in the infinite dimensional case. Then then the spectral theorem says that then there exists a orthonormal basis, right, that is the you can diagonalize T, right. So, there exists an orthonormal basis. So, let us say E j such that T E j equal to lambda j E j, right. So, lambda 1, lambda 2 etcetera are eigenvalues of T, right. So, T has an orthonormal basis consists of eigen vectors of T, right. This lambda 1, lambda 2 need not be distinct, some of them may repeat. Okay. For example, T could be the identity and so all of them should be just 1. Okay. So, let us look at spectrum of T. So, spectrum T is the eigenvalues of T, right, without repetition. So, this is a set inside the complex plane, okay. And the way to write the spectral theorem, one way to write the spectral theorem would be, if I take some lambda in the spectrum of T which is an eigenvalue, I have so yeah okay. So, I can write, so let us write the space H lambda to be the eigenspace corresponding to lambda. So, what is that? That is all x in Cn such that T x equal to lambda x, right. So, that is the lambda eigenspace of this operator T. Okay. Now, this if I the fact that T E j equal to lambda j E j, if I rewrite, what we are getting is the following. Okay. So, let P lambda be the orthogonal projection onto H lambda, right. So, P lambda will go from Cn to H lambda, right. So, the okay. So, the spectral theorem says that if you look at Cn, that actually decomposes into eigenspaces of the normal operator T, right. And we have these projections P lambda and they are orthogonal to each other. So, if I take two distinct eigenvalues, P lambda and P mu will be orthogonal to each other, that means P lambda P mu equal to 0 if lambda not equal to mu, that is same as saying that the eigenspaces corresponding to distinct eigenvalues are orthogonal to each other. But the because Cn sum of H lambda is Cn the whole space, that is also same as saying if I look at the sum of P lambda where lambda is in the spectrum of T, this is the identity operator, that is the whole thing, right. Any x, any z in Cn can be split into these pieces in H lambdas, and if you put them together you will get your z, right. And more importantly, the operator T is simply lambda P lambda where lambda is in the spectrum of T, right. So, P lambda will take everything to the eigenspace H lambda, and on H lambda T acts like multiplication by lambda, right, that is simple. Okay. So, this is what the spectral theorem says. Okay. So, this is what you can keep in mind. There are other ways of looking at it. I will explain maybe one more. So, let us say this is version 1, version 2 is so, let us take omega to be equal to 1, 2, 3 etcetera n. Okay. Then the space Cn can be viewed as all functions from omega to C, right, because f of f is determined by what happens to f1, f2, f3 up to fn, right. So, you think of that as a coordinate f1, f2 up to fn, you get a point in Cn, and any point in Cn can be viewed as a function from this set 1, 2, 3 n to the complex numbers. Okay. Now, let T E j equal to lambda j E j. Okay. Consider the function phi from omega to C, okay, phi of j equal to lambda j. Okay. So, phi is a function on omega taking values in the complex plane, and I am just defining it to be phi j equal to lambda j. Okay. So, where lambda j are the eigenvalues of t. Okay. Now, you look at this Hilbert space. So, look at L2 of omega with respect to mu, where mu is the counting measure on omega. Okay. So, just one way of writing it, omega is the mu is the counting measure on omega. So, strictly speaking, when I define a measure, I need a sigma algebra, but here it is a counting measure. So, you can take the sigma algebra to be the power set. Everything is finite, right? Omega is finite, it is a finite set. You think of omega with discrete topology if you want. Borel sets will be all open sets, which are all sets. So, that is the power set. So, that is sigma algebra, and you have a counting measure there, right. So, you look at L2 of omega with respect to that counting measure. Now, your phi is a function which is in L2, right, or phi is actually in L infinity of omega with respect to, right, because it is just phi 1, phi 2, phi 3, phi n, they are all finite. So, it is a bounded function. Any bounded function defines a bounded operator on L2, right. So, consider m phi from L2 to L2 as a bounded operator. Okay. How is it defined? M phi of, I take a function in L2 of omega. How does that look like? It is a f from, it is a vector in Zn, right, and m phi of phi is phi times f. Okay. So, phi times f, well, it looks a bit strange because it is actually quite trivial. What is phi times f? So, phi times f, well, it is a function on omega. So, I should tell you what is it at j, right. So, that is just phi j f j. Okay. So, in other words, so this is just lambda j f j. Okay. So, in other words, m phi, if I take vector z equal to z1, if you want you can write it as a column z1, z2, etc., zn, m phi of this, m phi of z would be, at each coordinate I multiply by lambda j, right. So, lambda 1 z1, lambda 2 z2, etc., lambda n zn. Okay. Write it as a column so that it is easy to see how this is, which is same as. So, this is nothing but you look at the matrix lambda 1 etc., up to lambda n and the column z1 zn, right. This is how m phi looks like, and this is the operator t, right, because t ej equal to lambda j ej, right. So, these are two versions. One is you have for any continuous function on the spectrum, there is a operator corresponding to it, or you can view your operator t as a multiplication operator on some L2 space, right. So, these are sort of versions of spectral theorem which admits generalization. So, we will see that for a general normal operator, bounded normal operator on a Hilbert space, we can use the Gelfand theory to sort of look at this version, okay, and we will not look at the second version, but we will see that they are all equivalent. Okay. So, this version which will split the, so the splitting one has to understand what it means, the Hilbert space into various eigenspaces. Strictly speaking, there are no there need not be eigenspaces, right. For a bounded normal operator on a infinite dimensional Hilbert space, you may not have eigenspaces at all. Okay. So, one has to understand what that means, but then you have these projections which adds up to identity, and the operator t can be thought of as multiplication by some function, right, lambda here on the spectrum. That is what we will be doing. Okay. So, for the time being we will stop, we will start with generalities for spectral theorem in the next lecture. Okay. So, let us stop here.